A two-stroke engine is one of the simplest, yet most mechanically intense combustion systems ever designed. It has no camshaft, no complex valve train, no separate oil sump, and yet it can deliver remarkable power relative to its size and weight. The defining characteristic of a two-stroke engine is fundamental. It produces a power stroke on every single revolution of the crankshaft. A four-stroke engine requires 2 crankshaft revolutions to complete one full combustion cycle. A two-stroke completes the entire cycle in just one. That means twice as many combustion events at the same rotational speed. In theory, this gives the two-stroke engine a significantly higher power-to-weight ratio. If you like similar educational content, please like, subscribe, and share the video with your friends. But how can an engine manage intake, compression, combustion, and exhaust in only 2 piston movements? The answer lies in how the piston and cylinder are designed. In a classic two-stroke engine, the piston does more than compress the mixture. It also controls the opening and closing of intake, transfer, and exhaust ports built directly into the cylinder walls. There are no traditional poppet valves. The piston itself acts as the timing mechanism. When combustion occurs, the expanding gases push the piston downward. This is the power stroke. But at the same time, several other processes are happening. The crankshaft is being driven. Fresh mixture inside the crankcase is being compressed. The exhaust port begins to open. Transfer ports prepare to introduce new charge into the cylinder. Unlike in a four-stroke engine, the crankcase is not merely a housing for rotating components. In most two-stroke gasoline engines, it acts as a pump. As the piston moves upward, it creates a vacuum in the crankcase. This vacuum draws in a fresh air-fuel mixture through the carburetor or intake system. When the piston moves downward again, that mixture becomes compressed inside the crankcase, ready to be transferred into the cylinder. The entire design is mechanically minimalistic but dynamically complex. This simplicity is the source of both its strength and its weakness. Fewer moving parts mean lower mass and mechanical losses, but combining intake and exhaust timing creates efficiency compromises. To fully understand how a two-stroke engine operates, we need to carefully analyze what happens during one complete revolution of the crankshaft. Everything occurs within 2 piston movements, one downward stroke and one upward stroke. Let us begin at the moment of ignition. At the top of the cylinder, the air-fuel mixture has been compressed. The spark plug fires, igniting the mixture. Combustion occurs rapidly, creating a sharp increase in pressure. This expanding gas forces the piston downward. This is the power stroke, the moment where chemical energy is converted into mechanical motion. Unlike a four-stroke engine, this happens every single revolution. But while the piston is being pushed downward, several other critical processes take place simultaneously. First, as the piston descends, it compresses the fresh mixture trapped in the crankcase below it. Remember, the crankcase in a typical gasoline two-stroke engine functions as a pre-compression chamber. Second, as the piston continues moving downward, it uncovers the exhaust port. Hot combustion gases begin escaping from the cylinder due to the pressure difference between the inside of the cylinder and the exhaust system. Moments later, the piston uncovers the transfer ports. These ports connect the crankcase to the cylinder. Now the compressed mixture in the crankcase flows upward through the transfer ports into the cylinder. This incoming charge helps push remaining exhaust gases out. This process is known as cylinder scavenging. In theory, the fresh mixture should completely replace the exhaust gases and remain inside the cylinder. In practice, some portion of the fresh charge escapes directly through the exhaust port before it closes. This is one of the fundamental efficiency challenges of traditional two-stroke engines. When the piston reaches bottom dead center, it begins moving upward again. During the upward stroke, the piston first closes the transfer ports and then the exhaust port. The fresh mixture is now trapped inside the cylinder and begins to compress. At the same time, the upward movement creates a vacuum inside the crankcase. This vacuum draws in a new air-fuel mixture through the intake system. By the time the piston reaches top dead center, the mixture inside the cylinder is compressed and ready for ignition. the spark plug fires again. The cycle repeats. Within a single crankshaft revolution, the engine has completed. Intake, compression, combustion, exhaust, all in 2 strokes of the piston. This high frequency of combustion events is the key reason why 2-stroke engines produce strong power relative to their displacement. However, it also increases thermal and mechanical stress. One of the most critical differences between a 2-stroke and a 4-stroke engine lies in lubrication. In a 4-stroke engine, the crankcase contains oil that circulates in a closed loop, lubricating bearings, crankshaft journals, and cylinder walls. In a traditional gasoline 2-stroke engine, this system cannot exist because the crankcase is used to compress the air-fuel mixture. It cannot be filled with oil. The solution is simple but imperfect. Oil is mixed directly with the fuel. As the air-fuel-oil mixture travels through the intake system, crankcase, and cylinder, a thin lubricating film forms on internal components. This film reduces friction between the piston and cylinder walls and protects crankshaft bearings. But unlike in a 4-stroke engine, the oil is not reused. It is burned along with the fuel during combustion. This creates several consequences. First, lubrication depends entirely on the correct fuel-to-oil ratio. Too little oil increases wear and can cause piston seizure. Too much oil increases smoke, carbon deposits, and incomplete combustion. Second, burning oil increases emissions. Traditional 2-stroke engines are known for visible exhaust smoke and higher hydrocarbon output. This is one reason why many countries restricted their use in road vehicles. Cooling is another major consideration. Because a 2-stroke engine produces a power stroke every revolution, combustion events occur more frequently than in a 4-stroke engine operating at the same RPM. More combustion events mean more heat generated per unit of time. As a result, pistons and cylinder walls experience higher thermal loads. To manage this, small 2-stroke engines often rely on large cooling fins for air cooling. Higher performance designs use liquid cooling systems to stabilize operating temperatures and prevent detonation or overheating. The simplicity of the 2-stroke design reduces the number of moving parts. There are no camshafts, no valve springs, no complex timing systems. This reduces mechanical friction and overall weight. But the design also creates inherent compromises. Imperfect cylinder scavenging, fuel loss through the exhaust, increased oil consumption, higher emissions, narrow optimal RPM range. The 2-stroke engine is mechanically minimal, but dynamically demanding. Its operation depends heavily on fluid dynamics, pressure differentials, and precise port timing. One of the most fascinating aspects of a 2-stroke engine is the role of the exhaust system. In a 4-stroke engine, the exhaust primarily removes combustion gases. In a 2-stroke engine, the exhaust system directly influences cylinder filling efficiency. When the exhaust port opens, high-pressure combustion gases rush out of the cylinder. This rapid expansion creates a pressure wave that travels through the exhaust pipe. If the exhaust is properly designed, that pressure wave reflects back toward the cylinder at a precise moment. This reflected wave can help push escaping fresh mixture back into the cylinder just before the exhaust port closes. This phenomenon is known as exhaust resonance or expansion chamber tuning. The expansion chamber is shaped specifically to manipulate pressure waves. Its geometry controls how waves expand, reflect, and return. When tuned correctly, it dramatically improves cylinder filling at a specific RPM range. This is why many 2-stroke engines exhibit a sudden surge of power when they reach their tuned operating speed. Below that range, performance may feel weak. Within that range, the engine becomes significantly more efficient and powerful. However, traditional 2-stroke engines suffer from one persistent issue: loss of unburned fuel through the exhaust during scavenging. Modern engineering addressed this through direct fuel injection. In direct injection 2-stroke engines, only air is transferred into the cylinder during scavenging. Fuel is injected directly into the combustion chamber after the exhaust port closes. This prevents fresh fuel from escaping through the exhaust. This solution significantly reduces hydrocarbon emissions and improves fuel efficiency. As emissions regulations became stricter, most road-going vehicles transitioned to four-stroke engines. Four-strokes are inherently better at controlling intake and exhaust phases through valves and cam timing. But two-stroke engines did not disappear. They remain valuable where weight, simplicity, and high power density are critical. Applications include lightweight off-road motorcycles, chainsaws and portable equipment, small marine engines, large marine diesel engines operating on a two-stroke cycle. It is important to note that large two-stroke diesel engines used in ocean-going ships are fundamentally different from small gasoline two-strokes. They use forced induction and controlled exhaust valves rather than simple port timing. Still, they operate on the same core principle: one power stroke per crankshaft revolution. The two-stroke engine represents an engineering philosophy focused on mechanical efficiency through simplicity. It sacrifices emission control and fuel economy for compactness and power density. It is a design that demonstrates how fluid dynamics, pressure waves, and piston motion can replace complex mechanical valve systems.